So I'm Michal Crosby, and I'll kind of talk about the Containerd internals and kind of like what Containerd is if you don't know about it and the different components that it uses. So like first off, in Docker 1.11, we integrated runC and Containerd, and basically runC encapsulates all the container execution and runtime bits. So spawning the containers processes, creating new namespaces, C groups, and all that fun stuff. And basically what Containerd is a runC multiplexer at the very basic aspect of it. But also it adds additional things such as managing the container's lifecycle operations and handling different events that happens during a container's lifecycle. So whether it exits with a 0 status code or something else, if you want to send a signal to it, or if you want to do more advanced operations like get stats or pause and resume it. And so when we were looking at building Containerd, like what were some of the reasons why we wanted to start this? And first off was we wanted to kind of decouple the runtime component outside of the Docker engine. And so this kind of allows us to have better like code separation and basically make the Docker engine not be able to run containers on its own, but have something that's small and fast like Containerd that handles all this complexity at the runtime level. And it also gets us the runC integration that a lot of people have talked about in the past with the spec work that's been happening around containers. And so by doing Containerd, we were able to kind of rethink of how a container supervisor works and the different like aspects that we could optimize or features that we could add, and be able to work on that kind of outside of the Docker engine code base where there's image management and different API calls, and just kind of focus on the runtime aspect. So when we're building this, like one of the big things that you have trouble with in like any supervisor is locking, because there are some stateful operations whenever you're multiplexing hundreds or thousands of containers. And if you have your code base littered with locks, like it introduces a level of complexity that's kind of hard for developers. So kind of as an open source project, you have a lot of people contributing to it, looking at it. Kind of a simple model is to use like a lock-free events flow for handling like API requests or different changes in state of the containers. And that's basically what the core of Containerd is built on, is this kind of events model, and that every action or state modification that happens for the supervisors or all the containers on the system is a separate task. And so when you're a developer going into the Containerd code base, you want to add like a new feature or something like that. It's basically all encapsulated in these individual tasks. Then you just kind of register them in this nasty switch statement. But you have one place to know like where all the actions that you can perform on the container, how the different state and lifecycle changes are handled. And so it allows a simpler programming model where we can still have concurrency, but also synchronous events lock-free, and it actually helps out on performance. So also when you're a developer, when you're like coding these different events, you have like different guarantees. So if you make any changes inside of a task in this event loop, it's all synchronous, so you don't have to worry about knowing what locks to hold, where to grab this lock, where to grab that lock, or when. Like you can just write your code and do everything you need to do and not worry about locking or the different aspects in the system. So the next problem is if you have this synchronous event loop, how do you start containers concurrently? And so we introduced a worker model, and this is more of like whenever we started working on it, rethinking about what needs to be done synchronously, what needs to be done asynchronously, or what can. And so starting of a container is basically split up in two parts. the first part is a create step where things are registered on a system, and make sure that you don't start the same container twice, you don't reuse the same ID, and that needs to happen synchronously. But the actual execution, like starting the process, that can happen async. And so we have these workers that you send your main like start task to the event loop, and then once it successfully registers the container, creates it, it adds this kind of worker task, and there's like X number of concurrent workers that will actually do the start of the container. And so like as we were working on this, like it's hard to find like a good number of like how many workers do you have, and like you'll see a lot of issues on like supervisors or something where people say, all right, I tried to start 200 containers concurrently and my system locks up, or all this stuff. And instead of enforcing people to write queuing logic at the higher layers, like we looked at and did a bunch of measurements on like what's an optimal number of workers that you could have to start containers as fast as possible without like locking up the systems or like slowing down execution. And so it turns out like you can start 200 containers, 200 like concurrently, just blast it, and you'll get around like 54 containers a second. But if you just do 10 workers, start 10 concurrently and process all that work, you end up around 71 containers a second. So it's actually faster to lower the concurrency when doing starts of containers. And a lot of the work in like optimizing performance in this containerd work was just like rethinking like what actually we have to do, where can we look at, maybe if we lower concurrency, will it get faster or slower? And so basically a big thing of starting containers is that it's very system, like syscall heavy, there's mounts, there's a lot of IO, so it really doesn't make sense at all to start 200, 500 containers concurrently. It's better just to start 10, 20, and then let those finish before starting more. And so that's kind of a big basis of what we built into containerd. And kind of like the final part of the architecture of containerd is we do have an extra process called containerd shim, and this allows containers to be daemonless. And so I think one of the longest running issues on the Docker project is like, how do I upgrade Docker and it doesn't kill all my containers? And so when we first started working on this, like we didn't have this built in, and I kind of like showed it to a couple people, and one of the people on our team, Tonis, he said, we're not solving real problems. And so like he pushed me to like figure out this daemonless container stuff. So what we had was, we have this shim, and it's basically the parent of all containers. And the shim gets reparented to system init. It's not specific to any like init, systemd, upstart, or anything. It automatically gets reparented to system init after we launch it. And it's basically the parent. It has a one-to-one relationship between the containers process and itself. So what basically happens is, even if containerd shim dies, it only affects one container, but it allows that containerd can die or Docker can die, and your containers keep running. And it's basically that the shim, like people expect a lot from Docker, like you expect you to have your logs and your exit status, even if it's dead or alive. And so this shim is kind of like the middleman broker that reports the exit status even if no one's listening, and it uses FIFOs for the container's standard IO. And so that allows us that whenever containerd comes back up or Docker comes back up, it can open those FIFOs on disk and get the logs out so that nothing's missed. And that's basically like how the shim operates. It kind of sits in the middle between the containers process and the higher layers, and make sure that they can go away, but when they come back, they can reconnect to logging and get the exit status and everything else like that. And so that's basically all I have for like the containerd internals right now. Arnaud's going to talk about how that's integrated in Docker 1.11. And at the end, if you have any questions, we'll both be up here to answer those.
So yeah, So with what Michael just presented, we have like this super elegant, super fast bottom layer to execute containers. So I'm going to show you what we did with that in 1.11, but more specifically what we're going to do with that in the future, which is much more exciting than what we did with it in 1.11. So Docker 1.11 that we released 3 weeks ago, I believe, relies entirely on containerd and runC for execution. So for those familiar with the code base and the architecture of Docker, previously, we were directly depending on libcontainer, which we donated a year ago to the Open Container project. And now we are entirely using containerd and runC for execution, which means that Docker Engine alone doesn't have any code to run containers. That's a pretty weird thing to say, but that's the reality right now. Like Docker Engine, when you type Docker run something, it just passes a message to the Docker daemon that prepares everything for containerd to run a container, and passes the message down to containerd to actually run the container and create the container. So there's so many possibilities behind that simple sentence that I could give probably a whole talk about it, but that's not the topic. So what does it mean for the user right now? So short answer is nothing right now. Still, it's pretty cool for a lot of reasons. So this is basically the architecture that we have in 1.11. So at the very top, you have the CLI talking to the Docker engine as usual. Behind the Docker engine sits containerd, which is another long-running daemon. And below it, you have one shim per container. This complexity is entirely hidden to the user. So if you haven't upgraded yet to 1.11, you won't see a difference. You're going to type Docker daemon, you're going to type Docker run, Docker pull, whatever. It's all hidden from you, no additional complexity for you. So 1.11 was a lot about focusing on correctness. As you can imagine, like replacing the execution piece of Docker was not a small task, and getting it right was the most important thing for us before anything else. So yes, there's a lot of features that we will be able to build on top of this, but first of all, we wanted to make sure that we get it right and that we don't break any users. Quality is always our main priority on any Docker release. So yeah, and without performance degradation, which might seem as a paradox given that we talked a lot about how much work we've been doing on containerd to get everything fast and to get running containers fast. But the truth is, we're still adding some architectural complexity to the whole thing. What you have between Docker Engine and containerd is network protocol, it's gRPC. We have extra processes. So of course, this comes with a hit, but we've done a lot of work in 1.11 so that, again, you won't notice anything. There is no performance degradation with 1.11 compared to 1.10. Even if we have this complexity under the hood. What you can see from a user perspective when you upgrade to 1.11 is that you have a bunch of new binaries. So it's the end of the era where Docker was a single binary. Sorry for the people who loved it, but we needed to make this jump someday, so there it happened. When you install Docker 1.11, you have 5 binaries. Docker, which is the CLI and the daemon as you know it, containerd, containerd CTR, which is the client to containerd, containerd shim that we talked about previously, and runC. So let's look at the kind of features that we will enable with this in the future. So all the things I'm going to talk about for the following of this presentation is not ready yet in 1.11. It's going to be hopefully in 1.12. But once I show you, I hope you'll understand why we did all this in the first place. Yep. So the question is, what's Docker containerd CTR? So Docker containerd CTR is the command line tool for the containerd client. So you can use it to talk to containerd directly. It's not really meant for Docker users. We decided to ship it nevertheless as part of the Docker distribution so that if there's issues with containerd that we need to debug into or investigate, we can have you type containerd CTR commands directly to hit containerd without going through the whole Docker daemon. It is not a daemon, it is a client binary. Shim is the small thing that gets run for every container and that keeps, basically monitors a single container and keeps the standard IO open for this container. well, it's not technically a daemon because there is one per container, but the lifetime of container to shim is bound to the lifetime of the container process. So think of it as a companion process for the container process itself. So I showed the output of analyze.l so that you could see the sizes of those binaries. The truth is we're working on this. For example, right now the container to shim, so you have one per container process, and as you can see, it weighs 7 megs. This is not going to be true. It's already cut down in half, and we're going to bring it down probably to a few hundred Ks, I guess, because right now it's written in Go, because it was just easier for us to get it right in the first place. After it stabilizes, we're going to rewrite it in C, where it's basically not going to weigh anything. Right? So a first look at what we can do from there. So the first thing is choosing your execution backend. So for those familiar with Docker and up to 1.11, there was a hard-coded set of supported execution drivers. So in the past, historically, you had the choice between two. You had what we called native, which was libcontainer, and you had LXC. Eventually, we ended up deprecating LXC because it's underused. But still, there was a huge appetite for people who wanted to introduce new execution drivers to the engine. And that's a problem for us because when it's hard-coded inside the Docker code base, it means that basically we have to accept gigantic pull requests to add execution backends to the engine, and we need to maintain this code in the end. So the great news about having this new architecture is that runC implements the OCI specification, meaning that anybody who wants to implement a compliant binary can go through the spec and just go through it and implement something different than runC. So runC in 1.11 is the default and the only one that you can use. And it's going to do what we do best, which is Linux native containers. However, there is a whole ecosystem of people looking at providing alternatives. So a few examples here. runV is a hypervisor-based runtime from a team called hyper.sh. runZ is super interesting. This is the Oracle people working on an OCI compliant implementation to work with Solaris zones, meaning that Solaris at some point will get native Docker using a different implementation than runC, but it's going to be the same daemon. And for those familiar with clear containers, this is a project by Intel that is providing basically a lightweight hypervisor, but hidden behind Docker. So you can still do Docker run, but what you get in the end is really a VM. So why is this cool for the user? Well, basically, the cool thing about this is that you can pick you'll be able to pick, hopefully in 1.12, on a per container basis, which execution driver you want to use. And the great news is that different execution drivers have different trade-offs. It can be in terms of performance, it can be in terms of isolation. I mean, there's a lot of things that we haven't imagined yet about what people are going to do with this. But for example, you could imagine something like saying that on all your Docker instances, you drop the runC traditional default execution driver, and for example, the clear containers drivers for running untrusted code with a better level of isolation because it's a VM around. And if you do something like this, you could imagine, for example, using Swarm to take decisions on whether you want to use this or that exec driver, depending on if the code that you're running is signed or not, if it comes from your team or not, or something like this. So that's really extremely valuable to the user. So hopefully that's coming for 1.12, and this is all allowed by this new architecture and having runC implement the OCI specification. Any question on this one before I move on? No? All right. So yeah, this is basically what's going to be possible in the end, having Docker Engine Containerd and Containerd orchestrating other things than runC, runC, runX, runY, runZ. Different trade-offs. Maybe some will be VMs, maybe some will be zones, maybe some will be whatever, who knows. Oh, actually, one example that could potentially be the future for run something is unikernels. Some of you who were at DockerCon last year know that we are now working, well, we acquired a company called Unikernel System with super system people. And obviously that is one way forward to having first-class support of unikernels inside Docker. So the next thing, so Michael mentioned it already. It's pretty clear from the beginning that container lifecycle should be independent of the daemon, but so far that wasn't the case. Ultimately, the goal that we want is that really Docker should never decide on stopping a container. This should be a user decision and never a system decision. So this is the issue number 2000 something. So Whenever something is in the 2000 for Docker, this means like prehistory. I don't know. It's like antiquity. It's still not there yet, but we're getting closer with this architecture. And this is exactly what I'm going to demo now, hopefully, if it works. So what I want to show is resilience of containers with this architecture. What happens when I kill the Docker engine? What happens when I kill containerd? So let's try this. This is not available yet in 1.11. If you take the experimental build, actually you can try this. So first, I'm going to run containerd. So Docker containerd is pretty simple. The only argument it takes right now, well, it takes several things, but the only thing I'm going to pass it right now is the path to the execution backend that I want to use. Here I'm going to use runC, traditional one. And I'm going to run nothing because my SSH session is down. And I'm going to run a Docker daemon pointing to that containerd. So again, this is not something that you have to do yourself. If you just run the Docker daemon as you used to, it's going to work. I'm just deliberately separating the lifetime of Docker containerd and Docker daemon so that I can show you what happens when I kill one of the two independently. So running the Docker daemon with overlay graph driver, nothing unusual here. Let me restart those sessions. All right, so I'm here. I have no containers running. So, the first thing I'm going to run is something that uses the terminal heavily. So I'm going to do a Docker runTI of one of the best images of all, 9cat. And there we go. So YanCat is running. Okay, it works. Notice that you have a timer on YanCat, which makes it very relevant to this demo. So YanCat is running. Nothing unusual here. I'm going to do a Docker PS. All right, it's running. And then I'm going to do something ugly. I'm going to kill the Docker daemon. So as you can see here in my list of processes, as expected, I have one daemon, which is here called Docker D because I'm using a build of a specific build of Docker. We have Docker containerd, which is the long-running daemon supervising the containers. I have one instance, which is my client displaying what's on top, and one shim, which is the companion process to the container. So let's kill this daemon. Boom. So I kill the daemon. Of course, my client loses the connection to the daemon. So the term on top, you can see that the connection is reset. Here you can see that the daemon died. So what I'm going to do now is restart my daemon. Nothing else. And let's see what happens here. Docker PS. Yep, it's up. It's been up about a minute ago. And the really cool thing about this is that now I can do anything that I can traditionally do with my container. I can do docker exec foo, it's up. And I can, for example, reattach. There we go, still there. So that's one of the things that we'll be able to do in the future. Other example, of course, is running something that matters more to people than YanCat. So let's say, for example, Redis. So this is the part where I'm going to use something for the demo that hopefully will go away in 1.12. I'm going to use --nethost because right now there is absolutely no way we can restart a container with a network stack after killing the daemon. But you can ping Madhu about this. He's working on it. So I'm going to run a Redis container. Nothing unusual here. Redis is running. I can show you that I can do things like --nethost. I can connect to my Redis, ping pong, all right. Actually, I'm going to do it from my host. Okay, so it works. Again, let's look at the processes, and let's kill the daemon. Daemon is dead, my client is still here, ping. Daemon is dead. So let's do things like let docker win and save on disk. And let's restart the daemon. Docker ps, Redis is still running. Docker logs Redis. I can see that all the actions that I did when my daemon was down have not been lost. I can see in the logs that, for example, somebody typed save onto Redis and the DB was saved on disk. And it's like nothing happened. I can do exactly the same with containerd. Docker containerd, /9, boom, ding, pong, like nothing happened. And I can relaunch containerd, and everything is back to normal. Docker ps. Yep, that's it. So one cool thing about all this is that, of course, the goal for us is that 1.12 is the very last release where you have to stop the containers to upgrade the daemon. If we do it right, it means that all the containers that you will run after 1.12, you will never have to restart them ever again. And yes, if we add new features to the daemon and if we add new features to Docker, those containers will not benefit from it, but at least they won't get stopped. True, the shim does. So the question is, do I really need containerd, the separation between Docker Engine and containerd, or is it really the shim that does the magic? It's true, it's really the shim that does the magic. The truth is, the Docker Engine code base, we needed to do something about it if we wanted to do something like this. The supervision code from the engine dates from basically 3 years ago, and it needed a rewrite, if only because there was just, the code was really extremely integrated, and performance-wise, it was full of locks in such a way that we couldn't be confident about this code. The containerd separation is good for us because in terms of maintenance and code quality, it's much better. It gives us a single responsibility binary that is much easier to test, both in terms of correctness, but also in terms of performance, which is something that we couldn't really do so far with the Docker daemon that has too many moving parts. And really, we did it in a way that we wanted to make it usable for people who don't really care about running Docker images and having the whole Docker experience out of the box, but just wanted to run containers. And containerd does that just fine in a way that is entirely decoupled from Docker. If there's any other question, that's all right. I'm going to give you mine.
Hey guys, my name is Madhu. I work on the Docker networking project. So it's a project named libnetwork, which we use in Docker starting 1.9. I'm supposed to talk about the Docker networking features in 1.11, but I want to start with 1.9 since we kind of revamped the entire networking stack in Docker starting Docker 1.9. So let's cover a few of the features that we added in 1.9. Then I will carry you guys back to 1.11, and then we'll do a demo on 1.11 and all the features that we are adding in experimental as well. So Docker 1.9 is the time where we added the Docker network UX, where network, all right. So network object became a top-level object in Docker, where users will be able to manage networks, whether it is within the host or multi-host, using various different drivers. This is added to support micro-segmented network features, where users should be able to create a network, attach containers to a specific network, and the Docker networking stack provides the guarantees that the container attached to a particular network is isolated, right? It is micro-segmented. It can be in a single host or multi-host. Regardless of that, driver will take care of that. And in 1.9, we also added the multi-host networking capability using the built-in overlay driver, which uses VXLAN tunnels. In 1.9, again, we introduced the third-party network plugins, where folks can write their own network plugins like Cisco, VMware, and others who have written plugins on Docker platform. So we can start using their technology as well. Containers can attach to multiple networks starting 1.9. So we have commands like Docker network connect, disconnect, as you can expect. You can have multiple networks. So a container can actually behave differently on different networks if required. Also, we introduced the IP address management. Users can actually write plugins for IP address management. So it's not just static 172.17xx. Now we can be anything that you prefer. And in fact, it can also be routable IP addresses from your network, right, using DHCP if need be. So I'll give a demo of that as well using the Mac VLAN driver. And also we integrated with Docker Swarm natively. So when Swarm comes up using Docker 1.9, we used to have the overlay driver used by default, and hence the containers across the cluster can talk to each other seamlessly, right? That was in 1.9. I'm going to switch to 1.10 now, and then we will, during the demo, I'll cover each one of the topic to correlate between these two. In Docker 1.10, we also introduced the service discovery concept, where now using embedded DNS. So now the Docker daemon in 1.10 also has a DNS server running there. So any container running in a user-defined network now can reach any other container within the cluster, within the network, using their names. So it's straightforward to write. You don't need an external service discovery mechanism for basic DNS reachability. And we introduced the long-standing feature for assigning specific IP address to containers. It was like, it's there for a long time, and why not, right? We added it now. With IPAM capabilities, we can support the --IP feature in containers starting 1.10. And we supported the alias feature, where a container can have a specific name, and you can have multiple aliases, so that applications can start using it in a way, if multiple containers can expose the same alias, so we can do a cheap load balancing, right, within Docker itself, which I'll demonstrate today. And the link support was not there in 1.9 for user-defined networks. We added it in 1.10. We also added the internal option in Docker network to isolate containers to just be within the host, and the containers cannot talk outside the host, right? For few use cases, people want to firewall their containers within a specific network. Multi-host networking was supported only in kernel 3.16 and above in 1.9. We added some fixes in 1.10 to make sure the overlay networks work across the kernels as well. And in 1.10, we had the proper integration with Docker Compose, right? So this came in 1.10. A lot of features we added in 1.9 and 1.10. So in 1.11, we actually stabilized the code, right? There are bugs, so we stabilized the code, and we added some long-standing features on the DNS itself. Now we support built-in load balancing using DNS round robin. In 1.10, we added the support for the DNS resolution, but we didn't support the DNS round robin. With 1.11, we added the support as well, right? Service discovery was not enabled for IPv6 addresses in 1.10. In 1.11, we added that. And in 1.11 time frame, we also added the MAC VLAN, IP VLAN drivers. I will demonstrate what that is for those who don't know what that eventually does. But theoretically, MAC VLAN, IP VLAN drivers are the gateway towards integrating your containers to the underlay, right? So the overlay driver that we added in 1.9 provides the an overlay capability where the underlying network is kind of hidden behind the scenes. So a container can talk to another container in the cluster, but if it has to be reached outside the cluster, we had to do the NATing and port mapping that we did before, as we did in the bridge case. But with MAC VLAN, IP VLAN drivers, we can actually expose your underlay VLANs right inside the Linux host, and you can actually place your containers in the VLANs that is managed by your underlay network, right? So this is awesome for the operators who still thinks containers are like VMs. So if they want to manage containers like VMs and you want to assign a specific routable IP address to containers, and who doesn't want to do any port mapping to reach a container, so we can do it with this one now. So a container can be reachable directly, routable within your underlay network, and you can seamlessly reach this container with no port mapping required and no NATing required, right? So that's the use case for this particular driver. So I'll demonstrate these capabilities now, and I have a few slides on various use cases that customers are trying to see Docker networking towards. If you guys have questions, we can cover that as well. Any questions so far, or should I just go to the demo first? Right, okay. Let's go to the demo. Right, so I have two hosts here, two VMs, Ubuntu VM and Ubuntu 2 VM, as you see here. And Docker network, as I said, is a new command line that we added in 1.9. So you can do an ls, you can create, connect, disconnect, inspect, so on and so forth. Let's start with the host one. So I configured this is running Docker 1.11.1 in experimental mode because I'm going to demonstrate the MAC VLAN, IP VLAN drivers, which is in experimental. We are looking for feedback from you guys. If you're able to try it out, give us feedback so that we can move it to production ready for 1.12. All right, so now I have already placed these two engines in cluster. So the design, the Docker networking overlay design is to support the engines by default to be in cluster. You don't need a swarm to manage that by default, but swarm is much better to manage it because you can reposition containers and so on and so forth. But even without swarm, we can actually create a network using the overlay driver, right? Let's give some subnet that we may want to use, like say, we give some name, right? OVNet. I missed the create command. There you go. So it created a network called the OVNet. So since the two VMs are in a cluster already, if you do a Docker network ls, you should be able to see the OVNet here as well, of course, because we use a KV store for synchronizing the states between these hosts. So those who are familiar with SDN, software-defined networking, they typically use a network controller to manage things. But in our case, we don't use controller. We use distributed state management using KV store. And we are working towards, on every release, we are working towards removing the KV store requirement and trying to do it without KV store. So hopefully by 1.12, we'll remove much more than what we have now. So with no KV store, things should work if everything is going the right way. All right, now we have a KV store running here. I use console in this case, which is not important. Let me run a container using the OVNet. Let's name it, say C1, and let's name it, let's call it demo1. box. Right, I'm running a container, demo 1. Now let's run the same host. I'm going to run another container, the same network, the OV network. Let's call it demo 2, and let's give an alias. Let's call it DB. Why not? So I have a DB container in this host. Let's run another container in the other host, Ubuntu 2. Let's call it demo 3, and let's have the same alias called DB, right? Now we have 3 containers. Let's look at the right. So demo 3 IP address is 40.1.1.4, right? Let's do the same thing here. All right, 41 and 3. So now what I'm going to do is I'm just going to do a Docker. Let's get into demo 1, and let's do a ping for DB. Right, so I ping DB, now it's resolved to 40.1.1.3, right, as expected. Let's try to ping some more. This time it's round robin, and it gave 40.1.1.4, right? That's because the way we do it is, if you look at the resolve.conf in the container that is running in an user-defined network, like an overlay network or a bridge network or any other network, you will see strangely starting 110, the name server will be pointing to 127.0.0.11. This is the embedded DNS that we have in Docker daemon. So any DNS request is actually, it will go to the Docker daemon, and from Docker daemon actually performs the DNS lookup based on the network availability and the containers that's available. And so based on this information, we're able to provide the DNS round robin as well, essentially, right? Now let me run one more container to just show the actual. BusyBox doesn't have a dig application, so let's do. All right, I'm going to run a specific image which has dig, so I can do a dig. As you can see here, if I do a dig DB, you can see that it's actually responding with the multiple A records, right, the DNS records. So this is what the application will make use of for doing the DNS round robin or whatever, right? So this is a simple example, but you can start imagining the applications of this one where if a container goes down, it automatically resolves to the next one and start working. So it will not, the application never stops. So this is the DNS round robin load balancing to be added in 1.11. But in 1.12 and later, they are planning to add more load balancing capabilities like virtual IP based and so on and so forth that you guys are aware of. So by doing this, we will be not opinionated about load balancing. We can let load balancing managed by the operators themselves, right? So that's the path that we are taking towards for load balancing and service discovery built into Docker, essentially, right? Okay, so this demonstrates the DNS round robin and load balancing. Okay, there you go. Look at the next one. All right, IPv6. Let's do a quick IPv6 thing and then we'll move on. For IPv6, I hate to type IPv6 CLI, so I'm going to copy paste things from here. Thank you very much. Right, so here I created an IPv6 specific network, so I can Docker network create, can specify whether it be not IPv6 or not for the network. In this case, I'm not using a -d overlay. I'm using a bridge network, which is within the same host, and I'm specifying a specific subnet for this network, right? So I create a network called v6net here. Now let's run a container. Okay, so I ran a container with some ridiculous name, ccc2. Now let's do a docker exec. Okay, it has an IPv6 address now based on our configuration. And now let's it's another container, right? Within the same network, v6 net. Now we can do a dig. So as you can see here, dig is a very powerful command, of course, for DNS resolution. You can check that when you say quad A is for the IPv6 based DNS lookup, essentially. So you can see that now we can do an IPv6 lookup, and it results in the proper DNS record for that. So you can do a ping 6. You can see that the ping works fine because the DNS resolution happens. And also the ping v4 should also work because, yeah. So so now as you can see, the Docker daemon can do both v4 and v6 resolution seamlessly, essentially, right? Okay, so that covers the v6 SD part. Do you guys have any questions so far? Yeah. Right. Yeah. So the question is, in the previous demo, using the overlay driver, we created 2 different containers on 2 different hosts, and the routing was able to happen seamlessly, like a magic, right? So of course it's not a magic. So when we created the overlay network, the overlay network actually creates a VXLAN tunnel between the hosts. And when you launch the containers on these hosts, when you do a Docker run --net on an overlay network, we use the KV store as a mechanism for registering the information that, hey, there's a new container has come up. But also we use surf. So surf is the way we use the control plane negotiation. So if you are familiar with networking protocols like BGP, OSPF, and so on and so forth, what we typically do is we exchange routes, right? IP addresses is exchanged between the routers, and the routers are able to do an IP address lookup, and then the traffic forwards appropriately. In our case, we use surf as a mechanism. Surf is a very extensive protocol. It's a gossip protocol. So in surf, we actually exchange the IP and MAC binding along with the VXLAN ID, right? So with that mapping, once we exchange information, every single VXLAN driver within the Linux kernel, we program the Linux kernel saying, hey, you know what? If you want to reach this particular MAC, take this VXLAN ID and then go there, right? So it's essentially routing in the overlay network. So once we do that, we do all the programming required. So VXLAN tunnel actually encapsulates your container traffic into an UDP tunnel and ships it to the appropriate neighbor, right? So it's essentially a surf gossip which takes care of it for you. Yeah. Yeah. Right.
Like for my laptop, my Docker club.
Okay, so good question. So the question is, in 1.9, 1.10, and even 1.11, containers running inside the overlay network are not directly reachable from outside the network, right? In fact, that's the idea. The idea of the Docker network is to provide the complete isolation for those containers, right? If users want to expose the containers outside, there are 2 ways of doing it, right? Today, we can do a port mapping, right? So when you do port mapping, what happens is, you know what, let's do it right now. Let me demonstrate that, so it's easy. Let's do a Docker network ls. Okay, so now we have this overlay network, OVNet, right? Let's do a I'm doing a port mapping of this on this port. Let's do a busybox. Sorry. Right. So now this is belonging to the overlay network now, but also I did port mapping. So what happens is When you do an if config within this container, you typically will see, whenever you run a container in an overlay network, you see two interfaces, ETH0 and ETH1, right? So ETH0 is the private IP address space where it's completely only within the cluster. You can talk only within the containers. But ETH1, as you can see, ETH1 belongs to the bridge network, right? So that's why when you do a Docker network ls, you also see one more strange network called the Docker gateway bridge, right? So the Docker gateway bridge is nothing but an external facing bridge. So when, as a user, you want to expose a container outside the cluster, the way to do it is, since we attach the container to the gateway bridge as well, the port mapping is exposed via that. Now we can reach the container through the gateway bridge, right? But as you can, it's all right. I will continue talking, yeah. All right, so what happens is, still we are using NATing and port mapping here, right? Since when traffic goes out, it will be natted out with the host IP address. And port mapping is required because we need to map the port on the host side, right? So that's exactly, it's a segue for the next driver. The next driver is the Mac VLAN driver, which is actually used to do direct and relay, right? Which I will showcase now. I'll showcase how that is done and how we can actually use the Mac VLAN driver to actually access the container directly without any port mapping or adding, right? It's in 1.11 experimental. So based on your feedback, we're going to, if it works, great. It works so far really well. If you, based on feedback, we'll move it to production in 1.12, hopefully. Yeah. The question is, in an overlay network, how long does it take for the container to be reachable by others? Okay, that's okay. There are a lot of things involved here, right? In a single host network, there's nothing to gossip, nothing to exchange, so it just works, right? But in a case of overlay network, it relies on the gossip mechanism, right? For it to exchange the information, for the reachability to happen. So the gossip is typically very, very fast. It's not like a BGP, it's a surf gossip, it's really, really fast. We haven't heard any issues with the latency of gossip itself, because the driver that we have is not just push, we also do the pull. So in a case where the gossip has not converged yet, we actually pull the information from the gossip, right? So at any point you won't see a failure or a TCP failure or whatever on the client side because the data is not there. Because if the data is not there, the packet actually reaches the driver. Driver pulls the data from the gossip layer. So at any point of time, even a single packet won't be lost. So. Right. So the VXLAN interface, it's a myth that VXLAN people have this concept that VXLAN is a full mesh and all those things, right? But VXLAN is nothing but a one-to-many tunnel. It's a UDP tunnel just listening on it, right? So creating UDP VXLAN tunnel is like creating your dummy interface. There's absolutely no delay in creating a VXLAN tunnel. Zero. So. Yes. So today we don't have the encryption enabled by default, but you can run IPsec tunnels and you can run your VXLAN on top of that if required. But we are actually looking at encrypted VXLAN tunnel as well by default, meaning you don't have to run your IPsec tunnel and run on top of it. Rather, we're trying to see if we can actually use the sec module to encrypt your data using the same VXLAN tunnel as an option. So we are working on it. Let's see how. So the primary thing in Docker, as you guys know, right, it should be easy to use and it should be at high quality, right? We don't want to be in a position where it's very difficult to configure. Then there's no point doing that in Docker. So we are trying to achieve that particular balance on how easy to use and how secure it is and things like that. Yeah, but we are working on that for sure. All right. Okay, so yeah. No. So the Linux kernel itself supports VXLAN driver. So we use the Linux kernel directly. But OVS is an option. And in fact, we have an OVS plugin as well, developed in the community. So folks have tried the VXLAN based on OVS as well. So yeah. Yes, of course, yes. So the VXLAN tunneling itself will have a 5% hit on the performance, right? Because we need to, of course, encapsulate. It's 5%, not more than that really. But one more thing to note is the MTU size. Since we are encapsulating the traffic in an VXLAN UDP-based one, it's going to increase the network header. So it's going to impact the MTU. So there's an open issue in Docker today, especially in VXLAN, that we don't support the jumbo MTU today. So supporting MTU is important. So today we support 1500 is the byte size, but there are cases in which folks want jumbo MTU where they know what they are doing with their network. So that we need to fix. So MTU and performance, like 5% hit will be there, and of course MTU will be smaller. Yeah. Right. Okay. Now let me cover the MAC VLAN IP VLAN driver, MAC VLAN to start with. Okay, so before going to the MAC VLAN, let me cover some use cases so people understand why MAC VLAN is in fact required, why such a driver is important, right? So the first use case we all know is the Docker 0 bridge. It's the basic default is there from Docker 1.0, right? Where containers are by default connected to a Docker 0 bridge. Whenever it wants, it does it exposes service using port mapping, and it reaches to the external network using NATing, right? This is the basic Docker 0 bridge use case that we all are aware of. Use case 2 is the user-defined bridge. It's same as Docker 0, just that we are actually segmenting them into different bridges, but the performance space is going to be exactly the same, where same IP tables, same port mapping, and same NATing done for external access, essentially, right? And it's very straightforward to create a user-defined network. Just do network create, you get it. Use case 3 is the overlay network. So here, this is what we demonstrate now, where, hey, you know what? A container can be attached to an overlay network, which by default has, they belong to two networks. One is the VXLAN network, another one is the default, the Docker gateway bridge network. Again, we use IP tables, NATing, and port mapping for external access, okay? This is the experimental feature for VLAN. It's complicated picture, but let me try to cover that, right? So as you can see here, what is missing here is the bridge. There's no more bridge here, right? In the MAC VLAN and IP VLAN drivers, there's no more bridge. Thanks to the support in the Linux kernel again, Linux kernel 3.9, I think, start introducing the MAC VLAN drivers in 3.9, and in 3.19, IP VLAN was introduced. Okay, but IP VLAN is not stabilized till 4.2, so caution: don't use IP VLAN in 3.19 kernels. It's really, really buggy. But MAC VLAN is very stable. So the idea of the MAC VLAN IP VLAN is that, as I explained before, you can actually plumb the underlay VLANs right into the Linux host. And once you do that, you can actually take the interface and plumb into the network, into the container directly. So in Linux, it's a convention, or if you look at the interface, when you create an interface ETH0.10, it typically means that it's a VLAN 10 subinterface of ETH0. Okay, so this is one possible use case of configuring it, where in the VLAN networking examples, we'll see that there are access ports and trunk ports. It's too much networking, I understand that, but just go with me on this one. So there are access ports and trunk ports. Trunk ports are the ones where we actually carry multiple VLANs in the same physical port, right? So now with this one, what we can actually do is we can actually have multiple VLANs configured on your physical network, and you can plumb them right inside the host. Now we can have segment. So the network operators, it's purely network operators essentially, where operators who have actually have the network already built using their VLAN paradigm, they can use the exact same paradigm into the container world as well. Right? They don't have to change the way they operate. They don't have to start thinking about natting and port mapping. It's very difficult for them to think in those terms because natting actually changes the IP address of the container. So they have tough time monitoring the traffic on the network. So there are a lot of scenarios why they want a routable IP address for a container, and they would be able to manage the containers the way they are managed forever, right? So those are the scenarios why the MAC VLAN, IP VLAN drivers come to really, really handy for the operators, essentially, right? Now, as you can see here, look at the command line here. It's pretty straightforward. You can do a Docker network create -d, the driver name, MAC VLAN, and provide the underlay subnet. So since you want a routable subnet, whatever subnet that you use in your network for your VMs, for your Oracle database servers, for your laptops, machines, you can use the same subnet here as well. And specify which parent interface you want the traffic to actually take, right? They can have 10 interfaces in your host, so you can choose which one you want it to be your parent interface. So once you specify that, that's all is required. We actually make use of the Linux MAC VLAN drivers for doing the rest of the magic, essentially, right? So to demonstrate this, I have, again, the same two hosts, but if you look at the E3, yeah, E3 is the interface I want to use for the MAC VLAN, right? As you can see, there's no IP address here because we don't care about IP address for this interface. Right, no interface. So now let's create a MAC VLAN network on both these hosts. In order to do that, I'm going to copy paste again. Let's look at it. So if you look at there's E3, but we don't see an E3 subinterface yet. So now when I create this command here, so I do a Docker network create driver MAC VLAN, and I give a subnet. This is assuming it's underlay subnet, and I'm specifying that even though the subnet is this, allocate IP address from the particular range, and the parent is E3.30, right? And I'm calling this MAC30 as a network name. Right? Network is created. Now, this is not an overlay network, meaning when you do a network LS here, we see the MAC30. When I go to the next host, when I do the same network LS, you won't see MAC30 here because we are not, the MAC VLAN driver is not a multi-host driver. It's a single host driver. I'll explain why it is a single host driver in a short while. So now the user can actually create the same type of network. You can name whatever you want to, MAC-foo, I don't care. But make sure the subnet, the IP ranges are two different IP range because we don't want the IP address to overlap between multiple containers in the network, right? Okay, so now I created two MAC VLAN drivers on two different hosts. Now let's run a container. Right? So now I created a container in MAC30 VLAN network. The rest looks exactly the same. So from a developer standpoint, we don't worry about how it is done. It looks like an 8.0 inside the container. The IP address is 30.1.1 because that's what we asked for, 30 network. Now I go to the another host. Let's go to the other host, and then I create, here it's called MAC-foo, let's call MAC-foo. And just creating a container again. Let's do ifconfig. You'll see 30.1.2.1 because the range that I asked for is 2.0 network, right? Now I can actually ping this guy. So if everything works well, it should ping fine. There you go, right? So now we are able to communicate between the two different hosts using the IP address of the containers natively without using overlay network, just purely underlay traffic, right? More importantly, what you should see here is I can do an NC command, right? Right, I'm listening on a port 8080, and I'm going to do NC 30.1.2.1 8080. Hi. Hello. Right. As you can see here, it's working now, right? So now, no port mapping required, no natting, right? Now, any container or any VMs outside the container can reach the container directly with no port mapping, no natting required, and they all belong to the VLAN 20 now, VLAN 20 or 30 or whatever, right? So this provides the full control for the operators to manage the containers in the scenario that they are looking for. So you can see here multiple scenarios. If you want to run the containers in Amazon, use overlay. If it is a private data center and they already have existing network with VLANs and they can't change the way they work, they can use the Mac VLAN drivers. And if you are okay with doing port mapping, continue using bridge. So we have all the scenarios that we are covering using these various drivers, essentially, right? So any questions on this? Mac VLAN? So Mac VLAN driver will definitely perform better, right? Because it does no encapsulation, right? And it's actually not even doing natting, it's not doing port mapping, nothing is done, right? It's purely raw Ethernet traffic going from container to the another container, like any other information, right? But if you use the VXLAN, it's a bit more heavy because we have to encapsulate. But VXLAN is much, much more easy to use because we don't care about how the underlay is built. It's overlay, so you can take the same network, you can run anywhere you want to, but you cannot possibly use this in Amazon, right? The Mac VLAN, because you just don't have access towards the VLANs configured by Amazon network, of course, right? So it depends on your use case and your flexibility that you want. So you can choose the drivers that best fit your needs, essentially. Yeah. It depends. It depends. Overlay cannot, of course, right? Jumbo frames is possible still. Depends on configuration. But here, yeah, as you can say, right, as you can understand, there are a lot of balance you can take. So overlay is much more for flexibility, essentially. While if you want to tweak the performance, you want to go deep under it, then start using the VLAN drivers and so on and so forth. Yeah. No questions? Yeah.
Subnet, but if you want to use subnet as a Docker overlay, it will be.
Yes, it's possible, right? So one cool thing about Docker networking is that a container can actually belong to multiple networks, right? Each network can be backed by different plugins. Okay, so now you can start imagining various scenarios now, right? Where you can actually have a router that belongs to the overlay network on one side and an underlay network on the other side. And you can use this network as the default gateway for you to reach somewhere else. That way, many containers can actually can run behind a particular router. The router actually belongs to both overlay network and an underlay network. Yep. Right. Right.
You can offer the access controls that
Yep, it's possible even today, right? So that's why we have this Docker network connect command, right? So in fact, I'll show it to you now. Docker network ls, you can do Docker network, say create test1 and test2, right? Now I have two different networks. test1, test2, both belong to bridge network, doesn't matter, just for explanation. Now we can do a Docker run. Right, so now if you do I'm running in test1 now, right? ifconfig, you see eth0 only, it's fine. Now I can do a Docker network connect test2 and take the container, right? Now I connected the test2 to another network. Now if you do an ifconfig, you'll see that there's eth0 and eth1 now, right? So now the idea here is the container can belong to an OLE network, and you can also attach a router to it, a soft router or a HA proxy or whatever mechanism you want to let the external guys in. And on that HA proxy or the proxy container, you can attach another network. The network can be an underlay plugin, like an IPVLAN plugin, right? That way, now that container becomes the gateway for the rest of the containers belonging into the OLE network. Yeah, exactly. So that's why the Docker network concept is simple concept, but you can start imagining how we can start putting them together, essentially. Yeah. Any more questions, guys? All right, that's it, I guess. Thanks.